Alrighty, welcome back everybody. This is going to be multiple choice question set B for Unit 7 for torts. If you guys are interested, the answers to multiple choice question set A, we're done with 1B, and you can see the answers here. And in our classes, we did the free responses. So the solutions for those are there in the content library under AP review session. Okay, so let's go ahead and begin and make the most out of our time. If you guys have any questions at any point, be sure to speak up. So it looks like we have some kind of pivot that a rod can move about, and we're going to have a lump of clay that is going to be launched at this. And so let's see here. A rod is at rest on a horizontal surface. One end of the rod is connected to a pivot that allows the rod to rotate around the pivot after a net external force is exerted on the rod. A lump of clay is launched horizontally toward the free end of the rod as shown in figure 1. The lump of clay collides with the rod but does not stick to the rod. The lump of clay comes to rest as the rod rotates around the pivot as shown in figure 2. Which of the following linear collisions is analogous to the rotational collision as described? So let's see here what we're thinking. Analogous means similar to. Okay. So if we look at this, our best answer choice is going to be D. We have a block coming in. It's going to strike a block at rest, and it's going to transfer all of its momentum so that this guy loses its momentum and the other object takes off. Now, because momentum is conserved, there is a direction for this motion. We had a net momentum to the right, so afterwards, if these two are the same mass, this guy will continue, the second block will move to the right with the same velocity to maintain that momentum. So answer choice D is our best answer choice here. Really important. If we look at this, the two blocks move together, not the case. The two blocks move together, not the case. These guys do not stick. Go ahead and look at question number 2. So 3 discs are concentrically attached to one another, and 4 rods of negligible match are attached to the outer disc. So we have one disc, a second disc, and a third disc. Identical objects of mass m naught can be attached to the rods, and their positions on the rods can be adjusted. The discs, rods, and objects form a system that freely rotates around the central axis that is perpendicular to the plane of the page. So as you are looking at this page, you have the axis coming out at your face or into the screen. They haven't defined the direction, but it's perpendicular to the plane of the screen. The objects are initially a distance d away from the axis of rotation. A constant force F naught is applied tangent to the second disc as shown in the figure. What the heck? Where's the third disc then? Because they're calling this guy the second disc. How can the system be changed so that the change in angular momentum of the system per unit time is increased? Okay, so let's see here what we're thinking. Alrighty. So we're trying to change the angular momentum. And so the angular momentum of an object is I times omega. And we're trying to change the angular momentum of the system as quickly as possible because they say it's the change in angular momentum of the system per unit time. Now, here, if we notice, well, this is the change in angular momentum as we were talking about. We can rearrange this in a certain way. We can write this as I times delta omega over delta t, which is really the acceleration. the angular acceleration. So in case we're wondering, well, why are we doing this? Well, we need to remember that the net torque is equal to the change in momentum over time, the rate of change of angular momentum with respect to time. So if we want to increase this entire quantity here, we need to exert a larger torque. So we're going to need to increase the net torque. Changing the locations of the masses just changes the rotational inertia. If we move them further away, the rotational inertia increases. If we move the objects closer, the rotational inertia decreases. But we're looking for the change in angular momentum per unit time. And so that will be the case here. They're looking for the net torque. Let's go ahead and continue here. We have a net torque that varies with time, and it reads, the graph shows or represents the net torque that a wrench exerts on a bolt as a function of time as the wrench turns the bolt around its central axis of rotation. What is the change in angular momentum of the bolt after 1,000 milliseconds? Okay, we'll go ahead and call it here. So we just said that the change in angular momentum per unit time is equal to the net torque. Now, if we look at this, we can go ahead and rearrange this equation so that the two variables occur on the same side of the equation, which is going to be the net torque times the time that it acts equals the change in angular momentum. And we have seen that if the two variables show up on the same side of the equal sign, and we see a little multiplication, this is a hint that we are looking for the area. So if we get the area of these two triangles, that will give us the change in angular momentum. In our notes, we said that the net torque changes the momentum with time. So we need to find out what is the net torque, and it varies. So we need to get the areas. So if we look at this, what is the shape? This is a triangle. The area is going to be 1/2 the base times the height, which is 1/2. The base is 1,000 milliseconds, aka 1 second. What's the height? The height here is going to be 6 newtons. And what we find out is that this is 6 times 1 is 6, divided by 2 is 3 Newton seconds. Now we may be wondering, well, that doesn't look very good. How do we rewrite this? Well, hopefully we remember a Newton is a kilogram meter per second squared. And then, so a Newton second here is going to be a kilogram meter per second. And so it still looks a little weird. But this is because we're looking for rotational inertia. So remember that this is kilogram meter squared for rotational I omega momentum. So here, even cleaning up the units doesn't look very good, but this guy here is kilogram meter squared times radians per second. So we should get something like this. So really our best answer choice is still C, even though the units look wonky. Oh wait, Newton meters, not just Newtons, Newton meters. I was missing the meters. Like, where did my meters go? So times meters, there we go. All right, question number 4. And just saw that we have a question in the chat. Yeah, I forgot the meter. Thank you there, I appreciate that. Sorry about that. Question 4. A uniform disk of mass m0 and radius r is mounted on a vertical axis so that it can freely rotate in a horizontal plane. This can be hard to visualize, so break it down. You know, it's just like reading skills. They tell us that we have a vertical axis. That means that it's going to be looking like a vertical line, and the axis is usually represented with a dotted line. so that it can rotate in the horizontal plane. So that means that we're going to have a disk that is going to spin such that it spins in the horizontal plane like this, like our XY plane. We have X, Y, and Z pointing out something like this, okay? The rotational, and this isn't terribly important, but a lot of people get hung up on the idea that they can't visualize it. The rotational inertia of the disk is I naught, and the disk is initially at rest. If a force is exerted tangentially to the rim of the disk for a time interval delta t, and the final angular momentum of the disk is L original, consider a second disk that has the same mass as the first, but its radius is 2 times r. So it's twice the radius. And the rotational of this disk is going to be 4 I naught. If the same force is exerted tangentially to the rim of the disk for the same time interval, then the final angular momentum of the second disk will be all right, we'll go ahead and call it here. So we have learned that the change in angular momentum is the net torque times the time interval that it acts. So if we apply the same force at the same distance, then maybe we would have the same amount of torque. But here we're going to have, well, let's go ahead and see here. Torque is R times F, crossed into F. So because we have twice the distance, the torque now is twice as much. We'll call this for B. Torque equals twice as much, the original torque. Now it's the same time interval, but so what ends up happening here is we're going to have the same amount of time as before, but now we have twice the torque because it's the same amount of force, but now it's acting at twice the distance. So B is our best answer choice here. The rotational inertia doesn't really have anything to do with this. All that's going to do is that's going to affect how fast this spins. But what we have seen is that for torques, the angular momentum depends on the torque and the time. And so we need to ask ourselves, well, how's the torque changing? Well, we're acting at twice the distance, so we have twice the torque for the same amount of force. Go to number 5. In an experiment, a torque of a known magnitude is exerted along the edge of a rotating disk. The disk rotates about its center and all frictional forces are considered to be negligible. Which of the following quantities should the student collect in order to determine the change in angular momentum of the disk for a specific time interval? And let me know if we have any questions so far. Alrighty, let's go ahead and take a look here. So we're trying to find the change in angular momentum. We know the net torque on this, or at least the magnitude of it. And so let's see here what we need to determine the change in the angular momentum for a specific time interval. The initial angular velocity of the disk, because this quantity is used to relate the angular impulse on the disk, not really. We can find the change in momentum without needing that. There are 2 ways to do this. we can say that the change in angular momentum is going to be the net torque times the time interval that it acts, and this is called angular impulse. Just like force times time was the gympulse or the impulse. When we talk about torques for some time, that is angular impulse. And so we could calculate it this way, or we could get the final angular momentum minus the original angular momentum. We don't really need that. The amount of time that the torque is applied to the disk, because the time interval is related to the angular impulse of the disk. I think B is our best answer choice. C, the mass of the disk, because this quantity is related to the rotational inertia of the disk. Well, that is a true statement. We're looking for, another way we can calculate the angular momentum is the rotational inertia times the change in angular velocity. So we would need, if this is the case, if C was even going to be remotely close to an answer, we would need the rotational inertia of the disk, we would need the final angular velocity and the original angular velocity. So that's like three things that we need to keep track of. Whereas here we already have the torque, and they want us to choose one quantity. And so that's too many quantities. The radius of the disk, nah. Okay, so B is our best answer choice. Let's proceed. I think I can zoom in for this one. Oh, wait. Oh, this thing has like positional zoom. 67 lessons later, I figured that out. All right. One end of a horizontal rod is attached to an axle that is connected to a motor. So I have my rod. Yep, that's a rod. And it's horizontal. That can be adjusted to change the angular speed of the rod as it rotates around in a horizontal circle. So it looks like we're going to be swinging this rod around. That looks dangerous. Let me make my rod a little smaller just for the sake of being able to fit the diagram. So it's attached to a little motor here. And it's going to swing this bad boy around in a horizontal circle, basically a helicopter. The students must determine the change in angular momentum of the rod after 10 seconds. And the students use the following procedure. 1, measure the length of the rod with a meter stick. Nice. Ensure that the rod is at rest. Nice. Start the stopwatch and simultaneously adjust the motor so that the rod rotates around the axle as the angular speed is slowly increased. Record the angular speed of the rod when the stopwatch reaches 10 seconds. Students are provided with the equation for the rotational inertia of the rod about one end, 1/3 ml squared. Which of the following steps should the students add to the procedure to ensure that the change in angular momentum of the rod can be determined? All right, we'll go ahead and call it here. So it looks to me like we have a fair bit of information. We know the length of the meters of the rod. We know that its original angular velocity is 0. We're going to have the final angular velocity and the time interval. And they want us to make sure that we can ensure that we can determine the change in angular momentum. So let's go ahead and take some inventory. So we have learned that the change in angular momentum, which is not this L, this is length, and that's one of the reasons why I try not to use capital L for angular momentum, but whatever. I usually actually used to write angular momentum like that. I should bring that back. But then people get confused when it's not shown up, but it shows up in college texts. Okay, so that's going to be I times the change in omega. And we already can find omega, that's the final angular velocity, minus the original angular velocity. So these guys are known. The rotational inertia depends on the mass and the length. We have the length. So it looks to me like we need the mass of the rod. D is our best answer choice. 1 second. Feast your eyes on this next question. I'm going to zoom out. All right. So we have a disc with a radius of 0.5 meter and a mass of 0.2 kilograms, and it is basically behaving as a pulley that will be torqued by the weight of a 0.1 kilogram mass. And they give us the net force here as a function of time. So it reads, in an experiment, a solid uniform disc of mass 0.2 kilograms and radius 0.5 meters, wow, is suspended vertically and can rotate about its center axle such that frictional forces are considered to be negligible. A string is wrapped around the pulley with one end and connected to a block of mass 0.1 kilograms and hangs from the string at rest as shown in figure 1. The block is released and falls to the ground as the pulley rotates. A student collects the necessary data to construct a graph of the net force exerted on the edge of the pulley as a function of time, as shown in figure 1. How can the student use the graph in figure 2 to determine the change in angular momentum of the disk from 0 to 4 seconds? Mm. All right, we'll go ahead and call it here. So as we have seen, oops, the change in angular momentum, man, these questions are getting old, is going to be given by the net torque times the time interval that it acts for. We have force and time. Well, we have time, but we can remember that torque. And as far as we know, there is no friction here. Frictional forces are considered to be negligible. And we have the net force. So the net torque is going to be R times the net force times the change in time. And so if we see, we have net force and time on the same equal sign, or on the same side of the equal sign. This is telling us get the area. And so we determine the area bound by the best fit curve and the horizontal axis from 0 to 4 seconds, and then we multiply the result by the radius of the disk. And so C is our best answer choice. Very nice. Remember, when we work with graphical methods, we almost never want to work with an average value. Even though an average value is okay, really, we want to work with the best fit curve. So that's why B and A are not very good. They sound so good, really. Like the main difference is just average value versus best fit curve if you look at these. And so because of that, it's not going to be the best way. There can be uncertainties that even the average value won't average out. And that's why your line of best fit minimizes these deviations. And so it's just kind of how the cookie crumbles. Let's go ahead and look at the next one. A student conducts. So very good. If you were thinking A, you're kind of on the right track. Let's look at D. Determine the area bound by the best fit curve from the horizontal axis and then divide the results. So the reason why we're going to multiply here is because if we notice, another way we can think about it is the change in angular momentum is going to be R times the change in linear momentum, which is P. So because of that, this is giving us the change in momentum here, that little area. But we need to multiply by R. And so, well, bad. Okay. A student conducts. Is this in the AP classroom? It should be. It should be multiple choice question set B. And then if you're curious about the solutions for the other parts, pre-response questions 1 and 2 were done in class today. And then a multiple choice question A we did last Friday, which was the asynchronous assignment for class for 8A, which at some point I'll need to reverse the card there on 1B and give them an asynchronous assignment out of AP Classroom. So a student conducts an experiment in which the data is collected about the net torque on the edge of a disk as it rotates about its center as a function of time. The student creates the graph that is shown. Before the net torque is applied to the disk, it rotates in the positive direction. The student makes the following claim. The change in angular momentum of the disk from 0 to 4 seconds is in the positive direction. Which of the following statements is correct about the student's evaluation of the data from the graph? Justify your selections. All right, we'll call it here in 4 seconds. Okay, let's go ahead and take a look here. So the student is correct because the net torque is 0. Not true. Yeah, we have a little, whoa, let's be careful here. Looks to me like the net torque is partially negative. Let's see here. The student is incorrect because the slope of the line from the data point at 0 seconds to data 4 is negative. No. Let's see here. About the angular momentum of the disk is in the positive direction. So the slope is not the case. We have learned that the change in angular momentum is the area. Anything with D, the net torque at 4 seconds, not quite. The student is correct because the area bound by the data and the horizontal axis from 0 to 4 seconds is positive. Okay, sounds maybe potentially correct. Let's see here. The student is correct because there is a greater maximum magnitude of positive torque exerted on the disk than the maximum magnitude of positive torque exerted on the disk. I wonder if they meant negative here, because they're making a comparison, and here they said positive torque, and then here they're kind of reword. So the idea here is if we get this area, hopefully we recognize that this area here is much bigger. It has a higher peak. It goes all the way to 5 versus 4, and it has a longer run, almost about 2.5-ish seconds, compared to about 1.25 seconds. So I think A is a better answer choice if it were worded correctly. Let me just check the College Board. That got signed out to see here if there was a mistake on this question. So really important. We're not looking for the slope. We're looking for the area. Oh, also, no, it's not this one. Because here they're talking about the maximum magnitude of the positive net torque, not the area. I'm sorry. I thought they were talking about the areas here, which is why I shaded that at no. B is our better answer choice because the area bound by the data on the horizontal axis from 0 to 4 seconds is overall positive, which is kind of what I was saying earlier. No. You are correct. If you chose B, unfortunately, you are correct. I believe there is a mistake there because I interpreted that statement incorrectly. And we'll in a second here, once AP Classroom loads, we'll share that answer with you. We have a graph of angular momentum, kilogram meter squared per second, and a function of time. And it reads: a student conducts an experiment in which a disk may freely rotate about its center in the absence of frictional forces. Nice. The student collects the necessary data to construct a graph of the rod's angular momentum as a function of time. My God, I thought I made mistakes in my questions. First, it's a disk, then it's a rod. Is this a shapeshifter? The student makes the following claim. The graph shows that the magnitude of the angular acceleration of the disk decreases as time increases. Which of the following statements is correct about the student's evaluation from the graph? Justify your selection. Oh, dude, I need to upload the physics 2 video. All right, we have about 10 seconds. All righty. Unit 6. No, that's... Wait, no. We're good. All right, we'll go ahead and call it here. In JP Classroom, nunca lo dio. No. Alrighty, loaded. Alrighty, so the student is correct because the angular momentum of the disk decreases as time decreases. That sounds pretty good. B, the student is correct because the slope of the best fit curve remains constant. That has nothing to do with that. While that is a true statement, that has nothing to do. Wow, that is pretty straight. Kind of impressed. Oh, dude, I copied over the one with the picture here. Shoot. That's the big one. Okay. I didn't delete it. So that has nothing to do with this. We're looking at a graph of angular momentum. It does look like in magnitude it decreases. The student is incorrect because the graph shows the net torque exerted on the disk is constant as as time increases. While the slope of this is definitely the torque and it is constant, no, that has nothing to do with it. The student is incorrect because the graph does not contain enough information to make a direct connection between the angular momentum of the disk and the angular acceleration. Hold on. Actually, I read the question wrong. I was going to say the magnitude of the angular acceleration of the disk decreases. The student is incorrect because the slope here is constant, and so constant. And if we look at the slope, well, the net torque is equal to the change in angular momentum over the change in time. So definitely the slope is constant, aka alpha is constant. Sorry about that. No. You guys are 100% correct. Those 4 of you guys. Very good. See, you guys are better readers than I am. The duplicate. Let's go with number 10 here. A merry-go-round disk with a rotational inertia of ID about its center spins around a central axle that has an initial angular velocity omega naught. A child is standing near the edge of the merry-go-round as shown in figure 1. The child's rotational inertia of about the center of the disk when near the edge is I naught. As the merry-go-round spins, the child moves closer to the center as shown in figure 2 until the disk rotates with an angular velocity omega 1. Which of the following equations should a student use to determine the rotational inertia S of the merry-go-round child system about the center axle immediately after the child has moved to the location shown in figure 2? Justify your selection. Okay, yeah, it was B. Alrighty. For about 36 seconds, let's go ahead and see here. So what's going on? Well, we want to consider angular momentum conservation. So let's go ahead and see here. Well, the disk is spinning, sure, but the child is also going around the merry-go-round, so they also have angular momentum. So we need to add up their angular momentum. And because the child is on the disk, rotating with the disk, they're going to have the same angular velocity. So we're going to want to add their 2 angular momentums here. They're in the same direction. And so because they both have the same angular velocity, moving in the same direction, then we can just add the rotational inertias by factoring out omega naught. You can think of it as the rotational inertia of the disk times omega naught plus the rotational inertia of the child, which is, I believe, I naught times omega, and we just factor that out. Now, they're going to have a different rotational inertia as a system once the child moves in, and then that'll be the final velocity. So C is our best answer choice. Number 11. Oh, yes, they have the same angular velocity here, and they're moving together in the same direction, right? The child moves closer to the center, but as far as we know, they always stay spinning with the merry-go-round. Okay, let's go to the next one. Question 11. Disk Y of rotational inertia Iy about its center is held at rest above disk X with rotational inertia Ix about its center. Disk X rotates about its center with an angular velocity omega 1. Disk Y is slowly lowered onto disk X until both disks are in contact and travel together with a common angular velocity. A graph of disk X's angular acceleration as a function of time is shown. Which of the following equations can the student use to verify that angular momentum is conserved in the situation? Alrighty, so what's the idea? Well, the only thing that was spinning at the beginning was disk X. So we can go ahead and say that, okay, that's the initial angular momentum in our system at the beginning. But now that we drop disk Y onto it, it is going to move and travel together with disk X. So because they move together, we want to add their rotational inertias because they're going to have the same final angular velocity. So here we can go ahead and kind of look at the solutions or the equations kind of like the previous answer choice. So here in this case, they're going to have the same angular velocity at the end. So we need to find an expression that correctly expresses the angular velocity at the end, because all of these guys are really omega final. Well, if we look here, we experience an acceleration. All righty. And so we can get the acceleration times time that gives us the angular velocity change, delta omega. And so if we look at this, it's the final angular velocity minus the angular acceleration at 5 seconds. That's this guy here times time is going to give it to us. The annoying thing here is it looks like it's T1, but we're really going from this time to this time, which from the looks of it is about, let's see here, that's 1, that's a half, that's 2 halves. Sorry. That's 1 half, 2 halves, 3 halves, 4 halves, 5 halves of T1. And this is 1 half of T1. This is 2 halves of T1 or T1. And this is 3 halves of T1. So when we subtract this, delta T becomes 5 halves T1 minus 3 halves T1. And that's what they're explaining there in the sentence, or 2 over 2 T1. So what bad? And again, let me know if we have questions. So we have the exact same scenario. This is actually visualizing what was going on. We have one disk at rest and one of them is spinning. And then they're dropped and spin together. A disk rotates about its center with an angular speed of 30 radians per second. That's absolutely fast. An identical disk is held at rest above the rotating disk and then gently dropped on the rotating disk as shown in figure 1. The two-disk system rotates with a common angular speed. A third identical disk is held at rest above the two-disk system. The third disk is gently dropped on the rotating two-disk system as shown in figure 1, and the three-disk system rotates with a common angular speed of omega 2. What is this value? Okay, so hopefully we recognize that if angular momentum is conserved, then all we're really doing is we're changing the rotational inertia here, which is going to cause this change in velocity. In this case, the rotational inertia of this object, of the two disks, is really 2 times the original rotational inertia of this guy. Okay, so this is really 2 I naught. And so when we stack these two, what we find out is that the velocity here, omega 1, is really 1/2 the original angular velocity. The I over 2 I naught is going to reduce to 1/2, and the i's cancel. So this guy here is originally going at 15 radians per second. And then all of a sudden, we're going to drop this guy. And so we have 15 times 2 I naught equals now 3 I naught, because they're identical, times the final angular velocity. And so really this becomes 30 over 3, which is 10. Well, bam. B is our best answer choice. Very good. Well, what we can think about is we have the 3 times the rotational inertia as before for the same angular momentum. So we're going to have 3 times less the velocity. Here we have a figure skater shown in figure 1. They have their hands out and they are rotating about 1 foot. And then they're going to bring their hands in. And it reads, an ice skater rotates in a circle about an internal axis of rotation. Figure 1 shows the skater with her arms fully extended. Figure 2 shows the skater with her arms partially inward to her body. And figure 3 shows the skater with her arms completely inward in contact with her body. Which of the following claims is correct about the angular momentum of the skater? All right, we'll go ahead and call it here. So the important thing here is we're not seeing any net external torque. What this means is that if there is no net external torque, well, then the change in angular momentum is going to be 0, or time is infinity. So it turns out that the angular momentum here is going to be the same everywhere, or through all 3 states. It is a conserved quantity in the absence of a net torque. What I don't like is that they don't say there might be friction here, which might cause her to slow down in her spin, but they use the idea of an ice skater to imply that there is no noticeable friction. So they're not explicitly telling you, but we can infer that from the scenario. Alrighty, question 14. A planet of mass MP orbits a star of mass MS as shown in the path as shown above as a result of Newton's law of gravitation. Which of the following predictions correctly describes the angular momentum of the planet-star system and the angular velocity of the planet about the axis of revolution as it travels? Excuse me, I'm so sorry. I'm starting to get sleepy, I guess. It's getting past my bedtime. As it travels from position X to position Z. Alrighty. So let's go ahead and see here. So very important, because the force due to gravity is perfectly aligned with the radius vector, there is no net torque. There is no perpendicularity between the force due to gravity and the distance here. It's always aligned, so there is no torque, which means that the angular momentum of the system remains the same. Now, as we move from X to Z, we're going to be moving faster. One way we can think about it is our rotational inertia about the star has decreased, We are very far away. The rotational inertia of a point mass is m r squared. And as r decreases, the rotational inertia is going to decrease as well by the square of r. So if angular momentum is conserved, which is I times omega, as this guy goes down, this has to pick up. So the angular velocity of the planet increases over time. It's going to get faster. All right, let's go to number 15. We have the angular velocity of a star. An isolated spherical star of radius r rotates about an axis that passes through its center with an angular velocity omega naught. Gravitational forces within the star cause the star's radius to collapse and decrease to a value less than its original value, but the mass of the star remains constant. A graph of the star's angular velocity as a function of time as it collapses is shown. Which of the following predictions is correct about the angular momentum of the star immediately after the collapse? Alrighty. So again, even though this collapse is due to gravity, the gravity acts along the radius vector. It's always the gravitational force is always going to be aligned with it. So because of that, that means that the net torque due to the force of gravity is a big old zero. That means that the change in angular momentum is zero, which means that the final angular momentum is going to be the same as the original angular momentum. So C is our best answer choice. Very nice. 16. A rod of negligible mass may rotate about a pivot such that frictional forces are considered to be negligible. A figure, or the figure, shows two cases. Case 1 and case 2, in which the two applied forces are of same magnitude, FH and FV, can be exerted on the rod. Which of the following two statements are correct about the net torque exerted on the rod? Select two answer choices. Oh shoot, this is a multiple correct. I gave you the choose only one. Okay. So if we look here, FV is going to create a torque in the counterclockwise direction, and it's going to have a lever distance or a perpendicular distance to that vertical force of this much. While the horizontal force here is going to have a lever distance that is much longer. Even though they're the same magnitude, these two forces are going to have different leverages due to their distances from the pivot. FV is much closer, so it does not create as much torque. The net torque exerted on the rod in case 1 will cause the rod to rotate in the counterclockwise direction. That is correct. The angular acceleration of the rod in case 1 is greater than the angular acceleration of the rod in case 2. Yes. Here, because they happen to have the same perpendicular distances, this is at 45 degrees. That means that this distance in the x direction is the same as the distance in the y. We use the y distance for the torque on the horizontal force. We use the x distance for the torque on the vertical force. And because those two lengths are the same, case 2 is going to have zero angular acceleration because the net torque is equal to 0. Ooh, I actually think, I think we're at an impasse. I think we have 3 really good choices. Let's see here if I'm making a mistake. So one of them is answer choice B, and the other one is answer choice D. Oh, shoot, I can't read. They said counterclockwise. No, this is clockwise. My goodness. clockwise. So not C. My goodness. So sorry about that. The net torque in case 1 will be in the clockwise direction. So yeah, B is correct. Okay. 17. Sorry if I'm kind of rushing. I was going to leave some time available for y'all to ask questions about anything. So a wooden board of unknown mass is placed on a fulcrum that remains in static equilibrium as shown in figure 1. One end of a string is attached to an object of unknown mass as shown in figure 2. Oh boy, where's figure 2? And can be hung on the board. I don't see figure 2. 1 second. Oh, there is no figure 2. Wow. Okay. They don't include a figure 2. Terrible. The question is, which of the following measurements should the student collect in order to make the verification? The students must mathematically verify whether or not the system remains in static equilibrium. Yeah, I think we're going to ignore this question just because we need figure 2. Let's go to this one here. A rigid disk with rotational, oh, sorry. Yeah, they messed up. A rip College Board, billion-dollar industry. A rigid disk with rotational inertia I naught about its center of mass is initially at rest. The disk is free to rotate without friction about a vertical axis through its center. So we're looking at it from the top because this dot here represents the vertical axis, and they do tell us that this is the top view. A constant force of F1 results in a torque tau 1 and is applied to the edge of the disk. The torque causes the disk to rotate as shown in figure 1. After a time delta T naught, a second force is applied to the edge of the disk, resulting in a torque of tau 2. Which two of the following corrections are correct about the motion of the disk after F2 is applied to the disk? Select two answer choices. Okay. We'll go ahead and call it. So here, if the net torque happens to be 0, that means that both of these create the same amount of torque. If we notice, this guy's going to create a torque in that direction. This guy's going to create a torque in this direction. So if those two torques are equal, then the net torque is 0, and there will be no change in angular momentum or angular velocity times inertia. So that one works out. Let's see here. If torque 2 is less than torque 1, the disk will continue to spin in the same direction, but with 0 change? No, there's still a net torque, so not this one. If the magnitude of torque 2 is twice that of torque 1, the disk will eventually come to rest and spin in the opposite direction with a smaller change in angular velocity per unit time than before. I don't think so, because we're going to have the same net torque. Let's see here. If torque 2 is greater than twice torque 1, it'll eventually come to rest and spin in the opposite direction with a greater change. There we go. This is going to give us a bigger acceleration. Here, this one would be alpha is the same as before because the net torque is still with a magnitude of tau 1. It would be 2 times tau 1 minus tau 1, which is just tau 1 in the opposite direction. Okay, and 19, and then we're home free. We have the net force as a function of time. A disk that can freely spin about a central axis is initially at rest until a net force is applied to the disk. The net force is exerted tangentially on the edge of the disk, which has a radius of 0.5 meters and a mass of that much. The magnitude of the force as a function of time is shown. Which of the following statements are correct about the disk? Select two answer choices. Okay. Oops. The final angular momentum of the disk is at 10 seconds is 12.5. Let's see here. Well, it's going to be 10 times 5. That's 50 newtons divided by 2 for the area. The change in angular momentum is going to be 25. So I don't think this one is correct. Unless I'm missing something, let me know. The angular impulse exerted on the disk from 0 to 10 seconds is 25 Newton meter seconds. That is correct. And then let's see here. The angular acceleration. Oh, I missed radius. Oh, shoot, get wrecked. That is correct. Thank you. And that is why. You're awesome. That is correct. So D is our best answer choice as well. Ooh, good. All right. I want to calculate slopes and then all that jazz. Yeah, thank you. Okay. So that's it for today. I mean, if you guys have questions, I'll stay here and answer them. I wouldn't stress too much about it though. Like, get some rest. More importantly, like, you're not going to magically learn something, I think, in the last 8 hours. Like, or really staying up late, you know, not, you know, try to have a de-stress. Any last tips? De-stress. Don't worry about tomorrow. You guys have the U.S. History EOC, and then you have the AP exam. Staying up to study is only going to hurt you. So just kind of, you know, have a little bit of fun and just take it with the best of intentions. Some of you guys have been putting in a lot of effort. I don't think I have to worry about y'all getting 4s or 5s. Yeah, the exam starts at 12 p.m. So you will need to have finished your EOC by then. It's going to be a mad dash. So yeah, I mean, we've done all we can. There's no sense in beating ourselves up over the scenario. I mean, I think I could have probably paced things out a little better so we could have gotten more practice in outside of these review sessions in class. But I think we've seen how class kind of plays out anyways. Outside of that, remember your principles. You know, forces will change velocities in the direction of the net force. AKA, they create accelerations in the direction of the net force, and the velocities change in that direction. Same thing with torques. They create angular accelerations that change the velocity in the direction of that acceleration. The direction of motion is defined by the velocity. This one, B and D. Oh, yeah. Because the impulse, the angular impulse is going to be 12.5. Yeah. So real quick, the slope of this bad boy is 5 over 10.5 newtons per, well, the net force is, let's see here, the angular acceleration is going to be, at 10 seconds is 40. So we take 5 newtons times 0.5 meters, that's 2.5 Newton meters. And then we go ahead and divide by the rotational inertia. Net torque equals I times alpha, and alpha is going to be 2.5 Newton meters all over the rotational inertia, 0.0625. And so let's see here, we can divide these over. 2 of these give us 12.5. 4 of these are going to give us 0.25 multiplied by a factor of 10. So yeah, B is our answer choice here. Any other tips? Take some peppermint. It really helps for the mind and clarity. Keep pace. Find the easy questions first. Don't get so hung up. Remember, you're only allowed like 1 minute and 45-ish seconds for these questions. So don't get so hung up. If you don't know it, either bubble and move on, or mark it and find time and gain time and pacing by doing the easier questions. The last 5 questions are multiple correct. That means that we got to get both of these correct to get full credit, which in this case, on this last question, I definitely did not do. Sorry, my eye is burning all of a sudden. You guys got this, you know. You guys, and not just to say like, oh yeah, you're inherently smart, but more importantly, you guys have put in a lot of time to this class. If you're just showing up for the first review session all this time, it's not going to make, you know, like much of a difference. It's all the little things that we do throughout the year that add up and make the difference. I used to take mints when you were in elementary. Yeah, so yeah, those little peppermints are nice, or peppermint based gum. Take a straight edge. and they will give you pencils, but they won't have rulers. You're allowed your calculator on both portions of the exam. You're not going to be doing a whole lot of calculations. It's mostly reasoning. So don't get too hung up putting in all those formulas into the calculator. It's only going to hurt you more often than not. You either know it or you don't, sadly. So yeah, I don't know. Other questions? Okay, you feel these review sessions helped? I'm glad. Yeah, you've been showing up to a good chunk of them. And so I think this kind of helps demystify a lot of the stuff that we were doing. Our class was more geared towards the calculation end of things. And when I felt like, okay, we don't really have time for all the calculations, I started shifting more towards the AP style questions because they're not all number based. They're more reasoning. Read the question, answer what the question is asking, because they love to play little gotchas like that. So definitely this, sadly, physics is an English test, basically. It's English and logic. Logic applied within rules of nature. But outside of that, I got nothing else. You guys can stay here, and if you have questions privately, you can ask them. Other than that, have a good night, get some rest. Don't stay up until all sorts of hours. It will be detrimental to you. Have a good one, y'all.
Thank you, sir. Have a good day.
Thank you.